And now we're back to recording. Okay, so this time around, we're not doing the master method or master theorem or whatever you want to call it. Well, the master theorem. Instead, we're going to do the actual recursion tree. The good thing about the recursion tree is that even if things don't break down evenly, you can see things for what they are. And I also like the fact that you can then analyze the recurrences by visualizing them as a tree, which is something that you can't always do with the master theorem or the substitution theorem, right? And this is not a matter of us guessing or approximating. We can actually see how the whole thing works. So now let me just do the screen share again, and let's take a look together at the recurrence tree for solving recurrences. Now, if you remember how trees work, okay, they have a certain anatomy to them. We'll take a look at what we have here. Here we have T of n, and this describes the recurrence at each stage. All right. So once you see how the breakdown works, you're going to notice that for each line, the recurrence changes ever so slightly, right, due to the actual branching. So in this one, we have a branching factor of 3, right? And the branching factor of 3 continues on regardless of how many times we reapply the same divide and conquer algorithm. All right. So as you can see, when we continue to do that, if we keep breaking things down over and over again, we're going to be looking at a breakdown of log base 3 of whatever this algorithm originally was. Okay. And this is what it looks like as it continues to break down and these different components start to add up for the work done at each level. You finally get to a point where you're doing only constant work. That's the part where you start to add things up and, try to take a look at the more optimized parts. So now here's the thing. For our tree, we have a height or a depth, alternatively, okay? And we'll say the following. So this is level 0, the very top part, and then 1 and 2, okay? So now if you remember about trees and how they work, in addition to branching, they have a height, okay? So now if we had a tree of, say, just this part up here, just one node, the height would be 0. But coming down here, the height now is 1 and 2, which is conversely the same as our depth. It's just a matter of perspective, okay? So now here's what it says about our different or our particular graph here, our figure 4.5. Here's the context. In a recursion tree, each node represents the cost of a single subproblem somewhere in the set of recursive function indications. To put that into terminology that's kind of clear for all of us, let's suppose that this were the merge sort, right? At each level, there's going to be a cost of a single subproblem. Well, remember that with the merge sort, we broke things into halves, right? So now at each level, we're going to be looking at the work done when we break the problem down into the smaller subproblems, okay? And so the recursive function invocations would basically be like taking the left half of our array and then, or taking, I should probably use as an example, oh boy, well, you know what? I'll just use the merge sort. So let's suppose that we're talking about merging, right? And we have two halves and so forth. And we're trying to build things back up, right? So if we were to break things down into smaller and smaller subarrays to compare things, which is not entirely necessary, but if we did, the breaking things down into smaller subarrays would be the part that allows us to, think in terms of the function invocation. In the case of the quicksort, if you remember, we said that the quicksort on average works roughly the same way. There's still an n log n, even if the partitioning doesn't go so well. The partitioning would be the invocation that would break things down into recursive functions, right? So that part would be, once again, the part where we look at the cost of a single sub-problem, okay, in the partition. With the merge sort, we did the same thing where we said, okay, we're going to work within this thing by, throwing in the first half of the array back into our algorithm and throwing the second half of the array back into our algorithm. So that's how it worked in that case, okay? And those are the recursive function calls. Now, there are others that we could have, like, for instance, binary search, the way we jump things into, halves and halves and then break things down. That also would be how we see our recursive function invocations, in which we continue to break down the arrays until we finally just have one or two elements left, right? So to actually, I guess you could say, see what's going on here, we'll say the following. The recursion tree is best used to generate a good guess, right? In the event that we want to sum the costs within each level of the tree, we're going to do that with per level costs. So as you can see right here, this cost is one thing, this cost is another, and this is another, okay? And then we start to see what the costs were. Here you see that we had C n square, right? And that was at level 0. But over here, where we broke into threes, right? Now you have the n over 4. So this would be n squared. And then the 1 over 4 would be our 16. And then you also have the 3 parts there. So you sum them up, okay? And you have 3 over 16 times C n squared. All right? Does that make sense to everybody? Let me just stop to see some hands. One hand, 2 hands, 3 hands, 4 hands. All right, let me put the hands down, and I'm going to ask this another way. Who needs to hear me say that again? Interesting. No hands. Okay. All right. Okay. So yeah, as you can see, there's work being done at each level. Now, the interesting part is the work done on each level, it breaks down even further. You see, over here we have at this level Cn squared. Now, when it branched down into 3 different components, right, what you see is the following. The Cn squared broke down into 3 different pieces. Now, the amount of work done was basically n over 4. So our b was 4 here, okay? But now, if you take a look at what you have going on here, coming down here, once again, you have the square of the fraction again. All right, let me stop to take a question. All right, yes, Evan.
Now that I think about it, I was looking at the fraction. I saw that it's n over 4 for
Mm-hmm.
like that second row. Why is it not n over 3, given that there's 3 fractions and not
Uh,
4?
yeah, well, that's a confusion of the C with the B, right? So the B is going to be specific to our actual problem, but the C is the branching that we did, right? So one is the time that it takes for the subproblem. The other one, however, is not the time that it takes for the subproblem, but how much branching was done in the division of the divide and conquer. So you had three subcomponents. Over here, you had a one, but there was not, if you want to look at it differently, let's suppose that this is n over 4 to the first, and this is n over 4 squared, right? This could be n over 4 to the 0, well, to some degree. If we say that the b part, right, which is the 4, was taken to the 0th power, then we have, something else for us to look at. So remember that B part where we were doing the A and the B and the C, and the C part was actually, like the multiplicity of the recurrence part with the branching factor, and the B was the total cost of, um, of the work done at that level. And then we had A, which was, um, oh boy, our A was, let me scroll down and go back to telling you what the A was. Let me make sure I got this so that nobody is thrown off. Um, okay, the A was the base of the, well, no, the A was the actual power of the base of the logarithm part, right? So in this case, we were doing the recurrence relation, right? We were talking about how many splits there were, and then the B and so forth. And we didn't do much with the letter C. All right. Um, Let me just make sure that I am not giving you, because here I believe that we did C times F of N. So we don't want to put those together because we were talking about multiplying some lesser function. So we were just using a different constant. So in this case, the A is going, or the C is going to cancel. The C is not going to be times F of N. It's going to be times the T of N, where T is our functional component, right? We're looking at it from a slightly different perspective. So if we were to look at it from the perspective of, 1/4 to the 0, then in that particular case, that would give us a 1, right? That's not, and given the fact that this whole thing, the way it adds up, there's not much of a breakdown or a subdivision or a subproblem. At this particular level, it's the most basic case, and we're just going to break things down further later on. It's when we come to these sub branches that, as you can see, the math becomes a bit more complex. We finally get down to the point where it's t of some constant, right? So let's just take a look of the entire breakdown in one case, and then we'll see if the questions persist. All right. So here they said the following. We'll be verifying this whole thing later. All right. So there could be some hit or miss here, but we'll be verifying it later. And if you're careful when drawing out a recursion tree, summing the costs, you can use a recursion tree as a direct proof of a solution to a recurrence. So that's the part that I, really prefer about, should the master theorem fail, if should we really need to do the recurrence, the tree is there for us. So in this section, we're going to, use the recursion tree to solve, make guesses, and so forth. All right. So let's suppose that we have the following. Here we have a case in which we have a recurrence relation, T of n equals 3t, n over 4, the floor of n over 4, plus,
Professor, are you sharing anything?
oh boy, yeah, I was just reading to you guys.
I don't
Thank you
see
for
it.
letting me know. Thank
Okay.
you for letting me know. I hope you were good listeners. I'll backtrack. Yeah, I just got so caught up in answering a question, I didn't like, go back to, I didn't go back to, okay, so here, let me help you to see what I was talking about. At this case here, right? There's no subdivision, so there's nothing to like split up or anything of that case. If anything is linear time, it's linear time. There's no sub case for us to like subdivide and see what happened in that smaller area. Okay, so you probably get to the point where in this part here, we have a subdivision. We divide this one again, and you'll notice that it's 1/4 and 1/4 and so forth, right? So if this were divided by a fourth, we get something that looks like this, and then something that looks like this, and then so forth, until we finally get down to this minimal case. And then you'll see that it's log base 4 of 3, right? Because the 3 is the sub-branching. And then here you have the log base 4, n to the log base 4 of 3, and that would be the total work done all the way across. Now, if you take a look at the height of this tree, we have log base 4 of n, all right? Whatever that full thing was. So up here, the height was 0, then 1, then 2, okay? And as you can see, it keeps pace with the actual exponent over this particular 1/4 part. So here we have the 2, this 1/4 as it is in the recurrence relation, that is a 1, all right? The 1/4 in this recurrence relation would have been raised to the power of 0. And then coming all the way down here until we just can't break it down anymore, we're going to have a log base 4 of whatever n was to begin with. So now, here we go. Taking a look, right? Here's the important part to remember. So let's suppose that we were doing the master theorem, and it seems nice for the recurrence relations that we want to solve. Here with the recurrence tree, yeah, we could take a guess with it, but if we do it just right, we could also hit it right on the head. So now let's see how we have a recursion tree that provides a good guess for the recurrence of Tn equals 3t floor of n over 4. The reason why we're saying floor is because we want to get a good integer out of it, plus theta of n squared. Now remember that this would be like a f of n type of thing. So the base, work for a function without the recursion. So we start by focusing on finding an upper bound for the solution. Because we know that the floor and the ceilings usually do not matter when solving recurrences, this would be an example of the sloppiness that they refer to. We could create a recursion tree. All right, so T of n equals 3t n over 4 plus cn squared. Now, let's take a look at that. All right, we're going to start out having written out the implied constant coefficient of c being greater than 0. If we were to write the actual tree, we would start as follows. This is the cn squared. All right. Now, moving further along, we know that should this thing break down, we're going to have cases in which we're going to have n over 4 work done in each subdivision. N over 4 work is done in that subdivision, and that subdivision, and that subdivision. Okay? So we basically divide it by a 4. Now, since this is already n over 4, n over 4 times that, once again, with 1 over 4, we get 16, 16, 16. Shouldn't be too bad, right? So far, we can work with it. Now, for convenience, we assume that n is an exact power of 4. Another example of tolerable sloppiness, so that all subproblem sizes are integers. Part A of the figure shows T of n, which we expand in part B. So here is T of n, okay? And our part A is right over here. Part B right there. And this becomes part C. And then finally, D. Don't associate the actual letters with like side-by-side diagrams. Associate them with the levels, okay? So first level, A, that guy there, that's T of N. It expands into part B, which is what we have here, right? That's going to clearly expand into C, but let's just take a look. So now part C shows this process carried one step further by expanding each node with cos T over N or T of N over 4 from part B. The cost for each of these three children of the root is C of N over 4 squared. All right. So we continue expanding each node in the tree by breaking it into its constituent parts as determined by the recurrence. So once again, this is C. And then finally, we're going to get to that part where at D, we're finally breaking it down all the way. So now constructing a recursion tree for the recurrence, T of N equals 3T of N over 4 plus C of N, or C times N squared. Part A shows T of N, which progressively expands into B through D to form the recursion tree. The fully expanded tree in part D has a height of log base 4 of N. It has log base 4 of N plus 1 levels. All right. So remember that the height is one thing. Right here, we have one level, but the height is 0. Get that? The height is log base 4 of N. It has log base 4 of N plus 1 levels. Okay, so depending on how you count them, the levels in the height will differ because of there being it's possible to have a height of 0 if there's no branching downward to another case. So now, because subproblem size is decreased by a factor of 4 each time we go down one level, we eventually must read or reach a boundary condition. So now, how far from the root do we have to reach one? And the subproblem size for the node at depth I is n over 4 to the I. Okay, so the subproblem size hits n equals 1, where n over 4 to the I equals 1, or equivalently, when I equals log base 4 of n. All right. I'm going to ask the following. Who needs me to break that down further? Be honest. No one. Mani, is that a yes or a no? Thumbs up sounds like it's all good, but if you raise your hand,
Yes.
it's okay. You need me to make a further breakdown. Yes? Okay, so
Yes.
okay, so here it goes. Let's suppose that we were looking at a binary tree. I guess we could do that, right? Binary search tree. Binary search tree. And what I don't want to do in this case is to somehow have abbreviated parts with the dot, because that's when it gets a bit more interesting and it's harder to really understand. So let's take a look at this particular tree right here. And we know that for a binary search tree that this thing is going to break down into a maximum of 2 children, all right? So we know that we would expect any traversal to be like a log base 2. But let's just take a look at the actual illustration, okay? And so we see here the following. This is level 0. If all I have is a root, then the height is 0, right? Uh, well, I should say this is level 1, but if all I have a root is the root, then the height is 0. Now, traveling down, this is level 2, which means that now I have a tree with a height of 1. Now I have level 3, level 4, level 5. Now, because I have 5 levels, I have a height of 4, right? Because this is 0, 1, 2, 3, 4. Everybody with me 100% on that explanation.
Could you go over
100%.
could you go over it one more time, if you don't mind?
Okay, so here's the root. Okay, the root is at level 1, but since we don't have anything else in our tree, just the root, we're going to say that the height is 0. Okay, now this would be level 2, level 3, level 4, and level 5. All right. However, we don't say that the height is 5. We say that the height is 4. If all we have is a root, then we don't have a tree of any meaningful height. So this right here gives me a tree of height 1, then height 2, height 3, and height 4, because I have a 5th level, right? If I ask you how tall is your skyscraper and all you have is, the ground floor, I mean, is it really a skyscraper or a tower? No, it's not. So if all you have is a root, you just barely have a tree. You have a trivial one, yes, but you don't really have much height to it. The level is 1 and the height is 0, because all there is the ground level. Does that make sense?
Yes.
Okay. Now the next thing is what follows. You see, we have a whole heap of elements here, and we know that this thing here, if the height of the tree is going to be 4, right? We know that the number of elements in this binary tree is going to be somewhat proportional, right? So 2 to the 0th is 1, okay? But now here we have 3. So we have 2 to the 1st plus 2 to the 0. Well, that gives us 2 to the 2nd minus 1. Now we have 7. That would be 2 to the 3rd minus 1, right? So the maximum number of nodes in a tree of height 5 would be 2 to the 31st. I'm sorry, 2 to the 5th minus 1, which would be 31 elements. Okay? Everybody with me thus far? All right, no complaints. So now, here's what they were saying about the breakdown. They say that this subdivision is going to keep splitting until we get a log base something of another number, okay, at the bottom, where it can't be split anymore. So let's suppose that we could not split 32 elements any further, right? Well, then let's take a look at how large that height would be. We're going to reverse engineer the definition. Okay, so reverse engineering that definition, here's what we're going to say. We had that part with the n over 4i. Let me just go back and read it again. Let me pull it out, and that way I can use the concrete example instead of abstraction. Okay. The subproblem size hit n equals 1 or constant, right? When n over 4 to the I equals 1. So now here's the thing. They said that we're trying to have n be divisible by 4, just to make it easier. But now take a look. the way we look at this is that the subproblem size for a node at depth I, where I is the depth, is n over 4 to the I. So n over 4 to the depth. All right, let's take a look at that. Here the depth is 0. So n over 4 to that depth would be n over 4 to the 0, which would be just n over 1, which is n. Okay, but now if this guy has a depth of 1, n over 4 to the 1, n over 4 to the second. Okay, now let's suppose that they said n over or log base 4 of n. Okay, so how do we take a look at that? Well, we need to do the following. We have a subproblem size for a node at depth I, where it is going to be, the subproblem size is going to be n over 4 to the I. Okay, now the problem size hits 1, this guy right here, when we get the fractions to balance out. Okay, now don't look at the whole thing. So don't start looking at like, oh, log base 4 of 3. We're not doing that. We're not doing that. We're just looking at how we got from this fraction here to somehow getting this whole thing to equal 1. That's what we're doing. So now, the breakdown. We get to that point with the assumption that n was already divisible by 4 by saying that, okay, there's a point where we just can't break this down anymore. But whatever this thing is, it's going to be, 4 to the depth of, 4 to the power of the depth that is I. And we need this thing to equal 1. Okay, well, how would we do that? Well, this is 1 over 4, okay? And we have 1 over 4 to the I. Now, if you remember how logarithms work, basically it says, I give you the base, you tell me the exponent of this that I need to raise it to this number. So now, here's how we put that into wording. I give you the base of 4, all right? You give me the exponent that I need to get to this guy right here. Now, that's not really pretty, but we're not really concerned about the 3 so far because that's just the branching factor. So let's just suppose that we're looking at the log base 4 of 1, which is this guy up here. All right. So we have something that is base 4. We need to get that 1 out of there. So here's what I'm going to do. I'm going to take this part right here, and I'm going to multiply both sides by 4 to the I. Okay, so now this cancels out. I have n equals 4 to the I. Interesting. So now, in what case would I have n equals 4 to the I? And what is this I that I'm looking for? Well, that I for its own part would require me to take log base 4 of both sides. Okay, once I take log base 4 of both sides, I'm going to notice that I is equal to log base 4 of whatever this n was. And the n part, when we say the subproblem hit size n equals 1 over here, right? The n part is this guy here, right? So now, here, let's try this again. I add all of these up, and I get n. But now, if I take a look at the height of this thing, log base 4 of n is the entire height of it all, right? So that's why they said the whole thing about that threshold of getting to I, okay? How do I get my 4, this part here, to equal 1? Well, I get it to equal 1 when I have log base n, or log base 4 of n, like I said previously, right? Because I said what I want to do is I want to multiply 4 to the I over here and then find out what I is by taking log base 4 of both sides. So if I took log base 4 of 4 to the I, then the 4's would cancel out and leave me with I. If I take this side on and you do log base 4 to the n, I'm left with log base 4 to the n. So I would then equal log base 4 to the n. Okay, now what does that mean? So over here, when we do that last case about, well, how much work is being done here? Up here, you remember that we had n squared. You had 3 over 16 n squared. So here was n over 4, n over 16. But now this here is going to give us a 1/4 to the 1 over 4 to the log base 4 of, well, 4, right? So that's going to give me a 1 here. When I add those ones up, I'm going to get n, right? So I'm going to get n times log base 4 of the 3 of, all of these, the 3 divisions that we had here, because we had to do work in each of them. All right. That's the actual arithmetic part there. So that's why they said here about that depth part where we just can't break it down anymore. That's going to be due to the subdivisions of log base 4, where you can no longer divide by 4. At what point can I no longer divide by 4? Once all of my multiples of 4 are exhausted and I'm just left with 1, right? So if it were 16, I can divide 16 by 4 twice, right? And that means that log base 4 of 16 is 2. As far as log base 4 to the I, whatever that is, I can divide that up I times. So log base 4 of 4 to the I would give me I. So now the problem size hits n equals 1 when we have n over 4 to the I for a depth I, the last level, right? Or equivalently, when I equals log base 4 of n, all right? Thus, the tree has log base 4 of n plus 1 levels at depths 0, 1, 2, log base 4 of n. Now, let's take a look at what we have over here. I was showing you this guy here, right? And I said that we have 5 different levels. So we can have as much as 31 different nodes, right? Down here you have 30, and then you have this one up here. Well, let's suppose that we were counting them out as, just saying for argument's sake that it's 2 to the 32, or just short of that. I'm sorry, 2 to the 5th, which is 32, or just short of that. So now the question is, at what point do we just have leaves here, where it's only one element and nothing below, and the tree does not multiply out to anything larger? Well, it's once we get to the part of log base 2 of the height of the tree, which is 5, right? So 2 to the 5th is 32. And I need to get to log base 2 of that 32 to get to the level where the leaves are in my binary tree. So that means I have to go 5 levels deep, right? But really, that means that I went to the level of log base 2 of 2 to the 5th, where I was equal to 5. Did you hear that? I was equal to 5, log base 2 of 2 to the 5th. Who got that part? Okay, who did not? It's okay, just let me know. Okay, Evan is being honest. That's fair. Here's some questions. Let's hear some questions. Evan, how can I help you?
guess just so I've been listening in. I guess my big question is just like I'm still not fully getting some of these exponents. It's kind of tripping me up. I'm just being honest.
Okay, no problem.
My
So, I
bad.
mean, it's okay, it's okay, it's okay. Nobody's all knowing. So here's the thing. So I should make clear, however, by the way, this is not a complete binary tree up here, so it doesn't actually have 31 nodes, okay? I'm just saying that that's the maximum it can hold if it had like 5 levels. But now, when it comes to the exponents, we're talking about the multiplicity or the division of the branching factor, which leads to that equation. So let's count forward, right? This would be 2 to the 0. This would be 2 to the first, just this particular level here. 2 to the second, all right? Now down here, we have a capacity of 2 to the third for 8 nodes total, okay? So now here we have, if we have a capacity of 2 to the third, this is going to be a depth or level of 3, all right? This guy is a depth or a level of 4. Capacity is 2 to the fourth, which would be 16 nodes on just this level. Now, adding them all up means that we're going to have not 2 to the fourth, but 2 to the fifth minus 1 nodes. Now, 2 to the fifth will be 32, right? So you have the 16 down here plus the 15 up here. So that gives us 1 less than 32, 2 to the fifth, 2 to the fifth minus 1. Now, let's suppose that we had to go backwards, okay? Because we're doing exponents and whatnot, we're not going to take roots of the number. We have to unravel the exponents. So if I told you that this tree has a capacity for 2 to the fifth nodes, going backwards, you would say 2 to the fourth, 2 to the third, 2 to the second, 2 to the first. But each time you're doing that, you're dividing by 2. If we divide by 2 over and over again, any number, what we're going to get in the end when counting the levels going up, however many levels that is, if we keep dividing by 2, that many number of levels, our outcome is going to be log base 2 of whatever that number was, which would give us the height of the tree, or I should say the number of levels in the tree, right? So let's take a look. I have 5 levels, and then I'm told that there's a capacity of 31. So, I know that there's 5 levels to this. If I divide by 2, I get 16. If I divide again, I get 8. If I divide again, I get 4. If I divide again, I get 2. If I divide by 2 once more, I'm going to get 1. Now, let's stop to think about it this way. How many times did I have to divide by 2? Well, this was one case. This was another case, a third, a fourth, and then finally a fifth case of dividing by 2. Coincidentally, log base 2 of 32 is 5, right? That is to say that 2 to the fifth is 32. So logarithm and exponents are the reverse of each other. Here, logarithm and exponent, exponentiation, as inverse functions. Okay. Here you have f of x equals 2 to the x. In the event that I want to know what this x is, I have to remove the base. Now, I can't just use any old logarithm. I have to use a logarithm that corresponds with this base here, 2, to remove the 2 out of the way and figure out what this exponent is. So that's why I'm going to use log base 2 of 2 to the x. Once I can do that, I'm going to get x on the outside, and I'll know what x is. All right? So basically what we did before is we said, hey, this thing is going to be 4 to the I. Now we need to figure out what that is, and the answer is log base 4 of 4 to the I, or log base 4 of that n that was over here. That tells us what that last place is. So instead of using concrete numbers, you're actually using the abstractions of the relationship. Now, here's why it works that way. Remember that if you add and multiply, you have two operands with the same relationship. All right. 4 times 4 is the same as 4 times 4. 3 times 4 is the same as 4 times 3. 2 plus 3 is the same as 3 plus 2. However, when you exponentiate, it's different. The relationship changes. You can't say that 4 to the third power is the same as 3 to the fourth power. So the way you split them apart is as follows. If you want to know what the value of the exponent was, right, you take the logarithm of the base. Here, this is the base, 2 is the base, x is the exponent. If I want to know what the value of the exponent is, I have to take the logarithm of the base. And that logarithm is going to have to be of that particular base. Now, if I want to know what the base is, despite the exponent being there, I have to take the root of this number here. So I would have to get the x root of 2 to the x. And that gives me the 2 back, right? So that's how that works. If I want to know what the x is, I got to take the logarithm. If I want to know what the base is, then I got to take the root of the exponent. The actual relationships are not one and the same. So they don't reciprocate. So there's two inverse functions for exponentiation and higher functions. So now, what does that mean? Well, if we take a look at what we have, let's see, is there any other way for me to try to show you without getting you too like warped or overwhelmed or anything of that nature? All right, here's one. So let's suppose that I wanted to know what the x here is, right? What I have to do is take the natural log of the e here, right? Natural log is a logarithm of base e. So I take the natural log of the e, and then I find out that x plus 3 is equal to, the natural log of f of x. And then I know that from there, I could say that whatever f of x is, or whatever the natural log of f of x is, if only I subtract 3 from there, I then can find out what x is. All right? So that's how you work with logarithms and exponents back and forth. Now, in the event that I was given a logarithm, let's suppose that this is, let's see. Let's suppose that I was given something like log base 10 to the x, right? And I want to figure out, let's suppose that this f minus isn't there. So we have a 5 equals log base 10 to the x, right? What I need to do now is exponentiate this thing, but I have to use the right base. So I'm going to say that 10 to the log base 10 of x will then be equal to 10 to the fifth. All right. So now if I work with that, the 10 and the log base 10 to the x cancel out. So then I have x equals 10 to the fifth. And when x is 10 to the fifth, sorry, when x is 10 to the fifth, the number that I get is 100,000. All right? That is to say 1 followed by 5 zeros. Is that clear? That's just how you do it with the inverse operations. Yes, no. Yes, Evan. Let's hear some.
Yeah, thanks for showing this. This is very good.
Great.
Thank you.
So here's what you need to remember, though. You need to remember the relationships between logarithms and exponents and roots, right? Because the thing is that, yeah, we talk about um, multiplication being repeated addition and exponentiation being repeated multiplication. But the thing is that the actual inverse operations, the way they build up, they don't hold with the same familiarity, right? Even if you went a little bit farther, and I'm not going to try to overwhelm you with this thing, but um, let's suppose that you had repeated exponentiation, right? Um, in that case, and this is just how operators and functions work in mathematics as you start to build up, right? So tetration, which is a repeated exponentiation, right? Now it has inverse functions as well. And, like I told you, somehow those operations, they no longer have the same relationship. So, we've moved beyond exponentiation, but we didn't get to the whole pentation level. That would be horrible. We don't want to think about that, right? However, when it comes to the actual inverses, the two inverses of tetration are called superroot and superlogarithm, analogous to the nth root and the logarithmic functions. But this is on a greater level. So as you can see, reversing the process becomes something different. So you see that? We're basically reversing the process of exponentiation. So, this is like, hyper operation type of mathematics, but yeah, that's how the behaviors between roots and exponents and logarithms work, because it's no longer that even relationship that you could easily understand when it was just a multiplication and division or addition and subtraction. Does that kind of show you why things are different? We'll have more practice, by the way. How you doing, Evan?
Yeah, yeah, thank you.
All right. But I mean, do you get like why we're doing what we're doing and how we reverse the processes with exponentiation?
Yes, yes, absolutely. It makes sense.
Okay, great. So that's where we need to get. We need to get to the part where it makes sense. That way, when you read the book, right, you can actually start doing it yourself and then like checking the work, right? It's always so much better when you check their work, because when you do that, you could then like, get a feel for not just the geometry, but the relationships on each level, right? So, how many people are with me with the understanding of how we build up exponents and how we go about getting logarithms? We'll just leave it at that for now. Uh-oh, show of hands, we have 0. Okay, Shafi, great. Who else? Let me just take a look at my participant. Okay, well, I got a few minutes to answer some questions. Let's hear some questions. No questions. Okay, so who just feels like they need to read the book closer? Oh, okay. Then who gets it 100%? George, great. Han, great. Okay, so let's see. What you need to do now is, I guess, study, right? Study that particular chapter because we need to like have that as a basis for what we will discuss. So here with these, you should be up on, right? Complexity classes, time complexity, space complexity, big O, big omega, theta, little o, little omega, um, the sorting algorithms, right? Why some of them are better than others. Let's see, the master theorem, the recurrence relations with the recurrence tree. I think that's plenty for you guys to actually work with. And since the exam is on Monday, you guys have, quite a bit to brush up on, but it'll be, I think, um, that's quite a bit of ground to cover. So that's not too bad. I wanted to get into matrix multiplication and the median of medians before moving on into other stuff. And hopefully a bit of string matching, and then moving into I then wanted to move into greedy algorithms and dynamic programming, and then get into intractable problems. All right. But I guess that's it for now, and I'll let you all go. All right. Now, here's my question for all of you. Tomorrow, do you want to do this thing online or in person?
Please in person.
Okay, so Evan says in person. How many for in person?
I'm fine with either.
Jahid is
Works for
fine
me.
with, okay, you're fine with either. Okay, so one person is for in person. How many for online?
I think I would prefer online.
Okay, so George says online. Jahid said he's fine with either, but his hand is up. Shafi says online. Okay, we don't have like enough people to like, there's how many still? Nine of us. Okay, so Alt Y or Option Y is for raising your hand. All right, here I'm gonna lower all the hands. And now, how many for online for tomorrow? Three, four. Keep the hands up. Four. All right, Han, what are you thinking?
Um, Either way is fine for me.
Okay, Manny, what are you thinking?
Either way is fine for me too.
Okay, Sabir.
Online.
Sabir? Online. Okay, so you're online. All right, so that's a tyranny of the majority online. But here's the thing. So Thursday is going to be in person. Thursday is in person. All right. Um,
Professor,
so yes,
would Thursday be all right to spend some time with review, like at least practicing something that might be on the test?
that's
Time
why it's in
classes.
person.
Yeah.
That's why it's in person.
I'm
Uh,
I'm
huh?
sorry. I'm confused. Is the test on Thursday?
Monday,
I
Monday.
see. I thought it was on Thursday.
Mm-hmm. Right. So Thursday, I'm going to be on campus. I mean, there can only be but so much tyranny of the majority because, I got to also keep like heads up for people being responsible. So, that's why I want it to be in person. I mean, I can record on Thursday, but, I got to be able to interact in a way that I know to be natural for people. So I got to go with the classical school method. And, yeah, that's what it is. So think of it this way. You had 2 days in person and 2 days online. All right. So tomorrow I'll see you online, but Thursday definitely in person.
Wait, what about the operating system class?
Same thing, in person on Thursday.
Uh,
Uh-huh. And it's online tomorrow. Yeah, there was another tyranny of the majority in the same class, and quite a few people are signed up to both. So yes, that's what it is. And I will see you tomorrow. Are there any questions about anything else? None.
Professor, Sorry, this is
Yes.
about the midterm again. What's your
Okay.
advice for like practicing for the midterm?
I think I said that already, but okay, so here goes. Let me just do a screen share then. All right. Let me just make sure I still have my Dropbox open. I do that. I think I do. Okay. So we're not yet done with recurrence relations. Here's what I want to do. Here's how far I want it to go. I would like to get up to the basics of matrix multiplication, right? But the master theorem and the recursion trees, we're going to finish recursion trees tomorrow, okay? You should know about space and time complexity. So the comparisons that we have between merge sort and heap sort and quick sort, you should know the trade-offs between them. Let's see. And speaking of that, you should also know about the different complexity classes, right? If I ask you to put the complexity classes in order, can you do that? You should be able to, right? And the fact of the matter is, it's actually pretty easy. Because let's suppose that you had to take n to the k or 2 to the n or, log base n, and these were actual numbers. You could plug them in, right? Then you should be able to see what they come out to be with the same constant. So, just being able to put them in order means that you have some sense of orientation, right? And that's what's important. Sense of orientation when it comes to how we're looking at this stuff. What's a polynomial time complexity and what's not polynomial? What's exponential, right? What about the case in which you have factorial time complexity? Is that exponential? Is it polynomial? I also brought up a subject that was, how did it go? I brought up polylogarithmic. What does it mean? Like you should be aware enough to understand stuff like that. You should also be able to understand the definitions of theta and omega and O notation, both big O and little o, big omega, little omega, and how they are defined, right? So, if you had to break down the actual way they look on a graph or the algebraic breakdown for why one is in O of another, could you do that? Right. So those are my questions, and you're gonna need some answers, but it shouldn't be so tough that you don't you never stood a chance. That's kind of ridiculous. I don't do that. All right. So there you have it. And when we talk about recursion and stuff like that and whatnot, sorry, you should be able to understand what's going on there. I mean, when you think about it, on the first day, we were talking about, well, what if when I do the binary search, what if I break things down into halves? And we're like, oh, that's log base 2 of n. Yeah, that's true. What if we broke things down into thirds, though? Well, then that's log base 3. What if we broke it into fifths? Well, that would be log base 5 if we kept breaking things down by fifths and fifths and fifths. So, these are things that you need to be familiar with. Does that work?
Question.
Yes.
Will this be open notes from all the notes that we've been taking recently?
Yeesh. I would like to say yes, but if I do, then the nature of the questions might be different. So, I mean, do you want straightforward questions or do you want questions where you got to think it through?
What do you mean by like that? Straight think it through, so like explanation.
Yeah, or like actually applying the principle.
Confused with that. straightforward question would be like, sorting what you just went over just now,
What's
right?
what's the advantage of this versus that? What's the complexity of this? Put these in order, that type of thing.
Those are straightforward, right? Yeah,
Yeah.
I think that's better.
Yeah, I think so too. And so, the thing is that you see, I can't ask you straightforward questions if you got your notes out. Um,
Um,
I would love to, but no, that doesn't do much of anything because it doesn't
Well,
show any understanding. Hmm?
what would the question that would make you think be like?
Okay, so now let's see. So let's suppose I gave you the definition of big O and um, big O notation. So what are the feeds, the n zeros of two particular functions compared to one another? Can you do that? The master theorem. What is the A, the B, and the C part? Um, that type of thing.
I see, like asking like the parts of the things we were
Like
taught.
like deconstructing things.
so if you ask those kind of questions, it'll be open notes.
I suppose so.
That works too.
I would
Do you,
prefer not
do you guys
open.
prefer that?
I prefer
Yeah, that
closed
sounds
notes in
good.
that case.
Okay, so you're thinking deconstruction rather than straightforward familiarity. Okay. All right. Okay, so I'll work on that. Sure. All right.
I would
Thank you.
like it to be straightforward and closed
Oh,
notes, honestly.
Yeah, me
I'll,
too.
oh, wait, did you say straightforward and open notes?
No, straightforward and closed notes and not open
Okay.
what
Okay, so
about both?
straight.
notes. That would be the best.
Oh, okay. So you want closed notes and breakdowns. Okay. Um, so let's see. As Sabir, you said me too to what? Me
I
too
think
to
step forward with close notes.
okay, so you would prefer the breakdown with the notes. Okay.
No. I'm saying straightforward.
Straightforward without notes.
Yeah.
Okay. All right. Yeah, I think that straightforward is like a better way to go because the thing is that, off the top of your head, you're gonna know certain things, right? And that's expected. However, if you have your references in front of you, like a real professional, you should be able to then break things down further, you know? So it's kind of like two opposite sides of the same coin, but the question is how far can you take it, or how far would you take it given the expressed expertise, right? So that's why I said what I said. Okay. But I guess what I can do is come up with some different questions and we'll take a look together. All right. But until then, you're all free to go.
Thank you, Professor. Have a nice
Thank you.
day.
Thank you.
Have a good
I'll see you
day.
all
Have a
tomorrow,
good day,
same
Professor.
time. All right. Take care. See you online.
Bye
Tomorrow
bye,
only though.
Professor.
Thursday, I'll see you in person.